Hi everyone, I'm Yosef Edery from the University of Jerusalem. I'm going to present suppressing BGP zombies without status transparency. This is a collaborative work of the Edery University, the University of Connecticut, and the College of Management Academic Studies. So let's dive in. I probably assume most of you know about BGP, but I will give a quick introduction. So here we have a simple example in which a client wants to send traffic to a server, which IP address is 1111. So basically, AS400, which provides internet to our client, wants to find the path to reach AS100, which is the origin of the prefix. So how does it work? So basically, AS100 sends an announcement to AS200, which is its provider. AS200 will install this route on its routing table, will pick the next hop on the AS path, and then AS200 should propagate it to AS300, and 300 do the same thing to 400. And now we have on our routing table a path to reach AS100, the origin of the prefix, and traffic of our client can be sent. So what happens if now AS100 wants to stop receiving traffic from AS200, this route we just created? So basically AS100 will send a withdrawal to AS200, this route will be removed, and the same thing, this withdrawal message would be propagated to AS300, and 300 do the same to 400. So one important thing is really important for AS400 to receive this withdrawal message, because if, for example, there is an alternative route, he should know about this message to reach the AS100 origin. So this is where the problem begins. What happens if AS300 doesn't propagate the withdrawal message? So this is what we call the withdrawal suppression, and as we can see, AS400 keeps sending traffic, as you can see here, to a route that no longer exists. The route is outdated. This phenomenon is called BGP zombies or stuck routes. So what I just explained, it was explicit withdrawal, but withdrawal can also be implicit. So let me explain this. So the same scenario in which AS100 sends a withdrawal message to AS200. However, AS200 found an alternative path to reach the origin, which provide with AS500. So instead of sending this withdrawal message, it would send an announcement with the alternative route. This is very common in BGP. And AS300, however, probably unintentionally, so because of some misconfiguration of the router, fails to propagate this announcement. Again, important to say that this can be unintentional, it can be intentional. So we will cover both aspects. And as we can see here, AS400, it keeps in its routing table a route or sends traffic to a route that is not the same that he has on its routing table. The path is not the same. And AS400 is not the only AS which got affected from this phenomenon. Also, all the ASes that appear on the customer con will keep this BGP zombie route on its routing table. So let's talk about the impact this has on the internet. So first of all, it generates suboptimal routing decisions, which adds latency to the data plane. Secondly, it creates a network instability. And worst of all, the packet loss due to routing loops. Regarding to routing loops, I won't dive in because of timing, but if someone is interested, I've prepared some slides to explain this. So I will explain a suboptimal routing decision scenario on the next slide. So coming back to the same example of the implicit withdrawal suppression, let's say, so again, AS400 sending traffic to a route that doesn't correspond of what he has on his routing table. And if AS400 has known about this route change, he probably would prefer to send traffic to do a route change and send traffic to AS600. As we can see, the path through AS600 is shorter than the one through AS500. So this is the suboptimal route example. And let's bring our solution. We name it route status transparency, and this is what this work is about. So the idea is pretty simple. To solve withdrawal suppression, we periodically send to a shared repository the route status that we announced, that we have on our routing table. And secondly, other ASes should retrieve that information from the repository to validate it. Also, as I explained, we also deal with faulty repositories. So this information can be authenticated using RPKI certificates. I will explain this on following slides. So one big challenge we have here now is that we have two different inputs now coming to the ASes. We have the BGP update message, and now we have the route status data from the repository. So there is a synchronization challenge here. And RoST solved this by adding a counter. So it will add the same counter to the BGP update message and also to the route status data uploaded to the repository. And AS will compare these two counters and rely on the information that is more recent. A second challenge is that we've checked on the data on the internet using route collectors, and we've seen that some IPs can have millions of route changes per day. So we don't want to, each time we see a route change, let know the repository about this. So what we propose is to do this to send the delta updates in batches, so periodically intervals. So let's see how this works. So with this example, so here we can see each AS has a local counter, which is unique for the prefix and the interface, which if whoever is not familiar with interface, it's just the relationship between two ASs. So here a counter is 17 for AS100, so we will increment this counter to 18 and add it to the BGP announcement. AS200 will do the same thing. From 35 here, we'll add we'll increment the counter and add it to the announcement. And AS300 do the same, and now AS400 has installed the route status and maps each interface with the specific counter. Let's say now that AS100 wants to stop receiving traffic from the route we just created. So the same thing, increments the counter, add it to the withdrawal. AS200 increments it, adds it to the withdrawal. And AS300 fails sending this withdrawal message. So now that we propose RoST, basically on the same, eventually on the next batch, AS100 will upload this route status to the repository, as we can see here. And the AS400 will retrieve this information and compare it with the route status learned from the announcement. As we can see, the counter is higher than the counter here, 18. So it will detect a withdrawal suppression. As I already mentioned before, RoST also deals with security. First of all, what happens if we have malicious repositories? So RoST uses RPKI certificate, can use RPKI certificates. RPKI is the mechanism to defend from prefix hijacking, which already has 55% of deployment. So basically, RoST uses this certificate. So the AS that uploads this information will use the private key of the certificate to sign the information. And repository and the ASes that want to retrieve information will validate this using the public key. Regarding to malicious ASes, to prevent the path manipulation and without suppression, RoST can be deployed using with BGP ISIC, which is a paper recently proposed, and this is explained more in detail in the paper. So again, the same example, explicit without suppression, and as I said, we can use our RPK repository, distribute the certificate through AS100, AS400, and the repository, and sign with the private key the information, add to it the signature. The repository will validate it, propagate, of course, the signature of AS100, and also AS400 can validate this information using the public key. So if we are covering the security aspect, there is one challenge in which, if we are sending this data in batches, as we explained before, because of the frequent route changes, we would need to sign every entry in the batch we are sending. And also, ASes are not interested on all the route status of all the internet because it is too much. They're interested on specific entries. So what we propose is to use Merkle trees. So how does it work? So basically, when we get to a new batch, the AS that uploads this information will generate a Merkle root and add it to the signature, will sign the Merkle root, and send it to the repository. And then if some AS want to retrieve from their information, so the repository will provide the Merkle proof for the specific entries. RoST has benefits under partial adoption against other protocols on routing protocols on the internet that don't benefit from partial adoption. RoST does. As we can see here, it's enough at least one AS before the suppressor to be adopting RoST in order to detect the suppression. So AS200 or AS100, enough to adopt RoST in order to AS400 detect the suppression by AS300. So we have simulated RoST under partial adoption. What we've done, we've used a CAIDA relationship to simulate the topology of the internet, and we've run this following scenario in which some origin AS announces a prefix, and after that, it sends an explicit withdrawal. And some tier 1 AS will suppress this withdrawal. So basically, on the y-axis, you can see the number of ASs that keep routing through this tier 1 suppressor, and on the x-axis, you can see the percent of ASs adopting RoST. So you can see that even if already 60% of ASs adopt RoST, we already have 80% of ASs in the internet detecting this suppression. So I will skip it because of timing. Yeah, so I will go to the summary. So basically, we've presented the problem, BGP without suppression, that creates some reroutes. So this has real impact on the internet. As I said, it creates suboptimal routing and also instability and possible routing loops. And we propose a solution, RoST, which ASs upload this information periodically, and other ASs will retrieve it and validate it from the repository. We cover also the security aspect. For this information will be signed using RPK certificate, and RoST benefits from from partial adoption and also can be easily deployed. Thank you very much. Questions?